Alright, so think about the word linear and what that means. You know, usually we're taught at an early age that linear means straight. So if you're looking at a line that is linear, or maybe an equation that represents a line that is linear, then that would represent a straight line, right? One of the first, I guess, easiest understandable equations of a line would be y equals mx plus b. This is the slope-intercept form of the line, right? We learned this at a pretty early age, and we learned that m is the slope, and we learned that b is the y-intercept. Well, in statistics, traditionally, we don't use those same variables. They're not even in the same order. We don't use the m, and we use the b, but we don't call it b, we call it b sub o. So in statistics, you may see a line written y equals b sub o plus b sub 1 times x, where b sub o, that's right, b sub o is the y-intercept, and b sub 1 is, of course, the slope. Alright, I'm going to show you an example from the book of what I'm talking about. This comes from page 199 in your ebook. So if we let b sub o equal 3 and b sub 1 equal 2, you'd have y equals 3 plus 2x. Now in your mind, if you need to switch that around and graph the line that way, then you can, but just understand in statistics a lot of times it's written like this, traditionally. Alright, so it's the same line, same slope, same y-intercept. It's just these two terms, I guess, are reversed, you could say. Sometimes it's pretty tough to figure out that line that we could write or we could draw to show the relationship. Your book gives an example of a set of data and just put some lines there. And it says, which line do you think best represents the set of data? Now, I could probably draw a line right now that would represent the data better. I could draw a regression line, or I could draw a linear graph there that would represent this set of data a lot better than any of those. You can tell A doesn't do a very good job, right? It's not even near the data items, so something, A shouldn't even be there. B does an okay job. C, it really does not really a good job in my opinion. So, it would be easy for me to estimate a line by just drawing one, through the center of data. But that's not what's done. There's actually mathematical formulas that you can use to find a line that best fits the data. Okay, and the way that that line is calculated is the closeness it is between the various data points. So like the distance that this line is from every data point is the way that the line is chosen, by whatever margin of error that you would have whenever you come up with your equation. So the actual formula is very intimidating because it's not easy, and that's why calculators or computer aided software usually comes up with the regression line. Okay, now if it's just a real easy set of data, then we could probably make a pretty good guess. I mean, of course we know the slope is positive. We don't have any numbers here on the x and y, so we can't really make a guess here. If we did have numbers on the x and y, then we could maybe guess what it is. Let me show you an example of what I'm talking about. Here's a data set that has x and y values. This is in your book on page 201. So this regression line, you can see we're looking at these data items and how close they are, or the margin of error here, to the line. So this is the line y equals 1 plus 0.7x. And you can see the observed distance from the point to the line, or from all of these points to the line. Those are all observed distances. The observed value. And then you have the predicted value. What will you get when x equals 4? So when x equals 4, you plug in a 4 right there and you work it out and you get 3.8. Well, here's x equals 4. You can see we're at 4. We're probably at about 3.8 if you go over. So it's pretty close. But this is the calculated value, this value right here. This is the actual value, 4.2. So it's a couple units off, but it's kind of close. So you can see why it would be very hard to come up with the values. I mean, you can't just take 2 points and figure out the line that goes between those 2 points. You'd want to figure out the line that has the least margin of error for all the points. And so whenever I show you this formula in a second, you're going to see why I said it's just scary looking. It is very complicated to figure out the equation of a regression line. Alright. So before we get into the scary equations, I don't want to scare anybody out this morning. Let's talk a little bit more about that margin of error. So your book took this equation here, this y equals 1 plus 0.7x, and it plugged in, it made a table. I'm going to put this table up here. So we're looking at that equation, I guess and this is on page 202. I might need to take that to the next page. Alright, so this is the X and the Y. These are the observed points that are on the scatter plot. Here are the predicted points. The predicted Y, we call that Y, and you see that little symbol right there? We call that Y hat. So that right there, that's Y hat. It kind of looks like it has a neat little hat on top. All right. And so what this table does is it gives the predicted Y what the value would be if you plugged in X equals 2, 4, 5, 8, and 9, because those were all the points that were in the data set. And then it takes the observed and subtracts the predicted and gets a margin of error. And they get the margin of error for every point. And then they sum all of those up. And you see the margin of error, it says, is negative 0.6. Now, what a program would do, or a calculator, it would sum all of those up and try to get 0. Okay, so that it's just by hand. There are ways to do it, but it is terribly complicated for large data sets. That's why we use technology. Just like if you actually wanted the variance of a set of 50 items, you don't sit down and write out all those 50 numbers. You do it in a program or a calculator that'll do it for you. Okay. So the error is the observed Y minus the predicted Y. That's where this error comes from. Observed, that's the actual data item that's in the set. The observed Y minus the predicted Y. Hello? How are you? Alright, well, if we were to use this margin of error to kind of help us correct a little bit, to help us correct our graph, we could let Y equal, now we have our y-intercept b sub o plus b sub 1x, and then we could add that little margin of error there to help fit our regression line there better. Now, once you acknowledge the possibility of error, you may see this written as y hat equals b sub o plus b sub 1x. Now that little margin of error is going to affect your other constant. And so if you have the equation written like this, y hat equals, that just acknowledges the fact that you have added in a margin of error. That's what the p hat means. The sum of squared errors, you see that in here? This column here, the error squared, just takes the error and squares it. You know what that does, that makes all the values positive. And you can see how you get that. You just take y minus y hat gives you the error, and then you square that, you get what's called the sum of squared errors. It can be used as a criterion for selecting the best fitting line through a set of points. If that, the sum of squared errors, is 0, then the model fits the data exactly. And the observed data must lie in a straight line. So you know, whenever you learn how to graph lines and you're putting a bunch of points up there and then you drew that straight line, if the sum of squared error, if this right here equals 0, then your linear or straight line will go through every data item. That usually doesn't happen. Alright, the method that we actually have to use to find that line is called the least squared line. Since it has the smallest sum of squared errors. The least squared line. Alright, and that we pick up in the next section.